Hello, in this video we're going to look at partial fraction decomposition, repeated linear factors. So repeated linear factors supposes that you have a rational expression, the degree has to be bigger on bottom, and that its factorization would be, let's say hypothetically that it's ax plus b times ax plus b squared, and it's all the way down to ax plus b to the nth power. Actually, to be a bit more specific, we're saying that the g of x actually would just be the product of ax plus b raised to the nth power. Let me clarify that. So what we'll do is for each repeated linear factor, it's going to get its own unknown constant, a1, a2, a3, and so on. And the trick is like, how do we solve these? And in previous video, we said that we have to combine like terms using the common denominator. But one way that you could do it is just by multiplying by the denominator. In this case, g of x on both sides, and it should work out to where we can just solve the partial fraction decomposition of it. Now, before I mentioned that what would we use this for, right? And what we might use this for is perhaps like if we have 2x plus 1 divided by x plus 1 to the second power multiplied by x plus 2, and then this is dx, right? Now, the expression 2x plus 1, because it's lesser in terms of the leading term and its degree than the bottom, then we know that partial fraction decomposition may be applied. Okay, so in this case, it's like we have a little mixture of, we have a linear factor, and then we have a repeated linear factor. So in this case, we have that for the setup, we'll have a over x plus 1 plus b over x plus 1 squared plus c over x plus 2. Now, this might seem a bit more complicated than the previous examples, but it's not going to be too bad because if we multiply by the LCD, which in this case would be the product of, x plus 1 squared and x plus 2, and we just multiply this whole thing by x plus 2 squared, it's x plus 1, sorry. Okay, so it's x plus 1 squared, and we'll just do this. So x plus 1 squared times x plus 2. Now, what that's going to look like when you simplify the algebra, like once we distribute across the addition for each one, then in any case, we get the following. We get the equation 2x plus 1 equals to a times x plus 1 multiplied by x plus 2 plus b times x plus 2 plus c times x plus 1, but to the second power, right? Now, in our previous video, we said that when solving for the unknown constants, we need to plug in values. This is true, right? So we need to plug in values, of which in any case, the most convenient one would actually be x equals to -1, which in any case, if we plug it on the left-hand side, that's going to be -1 equals to b times, b times -1 plus 2, which is actually just going to tell us that b equals to -1. So we found what b is equal to. Okay. Now, think about other values of which that we could plug in, and that value could be perhaps like x equals to -2. So we plug in -2, And we see that when we plug in negative 2 on the left-hand side, you get negative 3. But notice that when you plug it in, that the negative 2 cancels out the x plus 2, and then over here, it actually tells us that we end up with that c multiplied by negative 2 plus 1 squared, and we get that c is equal to negative 3. Okay, but now we need to find basically a. And how can we find a? And we'll just scroll up a little bit. Well, how we're going to find a is by plugging in x equals to 0. So we plug in x equals to 0, and we get 1 equals to 2a plus 2b plus, well, 0 plus 1 squared is just 1, so that's going to be c. But we already know that 2a minus 2 minus 3 equals to, well, in this case, 1. So we have that this is going to give us negative 5. So we have 2a minus 5 equals to 1. But that tells you that 2a equals to 6, which means that a actually equals to 3. Now, how this helps us is that it actually gives us now the ability to integrate the rational expression, because now we know a, b, and c. So we can go ahead and go back and plug these in, right? So we can do that, and we'll just scroll up a little so that way we can start writing out our rational expression. So we know that this is going to be the integral of 3 divided by x plus 1. And what was b? b was minus 1 over x plus 1 to the second power. And then this is going to be minus 3. Okay, so it's minus 3 over x plus 2. And then what was this with respect to x, right? Okay. Now, in terms of integrating each of these, well, we know that basically if we use u substitution for each of these three, that we'll get essentially the antiderivative, right? Now, normally, we can say that, okay, well, yeah, if it's a constant plus a variable x only, then of course it's just, it's due to chain rule or u substitution. It's just u is x plus 1, so that means that du is equal to dx, if that makes sense. So what I mean by that is, we can actually just say 3 times the natural log of x plus 1. But notice that here, you're going to take the antiderivative of this, right? So when you do that, using your u substitution, so like if you really need to do that, like where you say u is x plus 1 and du is dx, well, in any case, this becomes negative 1 over u squared, which in either case, we know that that's negative u to the negative 2. Now it makes more sense that, okay, when I do the integration, or the antiderivative, anti-power rule, we get 1 u to the negative 1. But that's really just 1 over x plus 1. And then similarly, we just say that the next one is going to be minus 3 natural log of the absolute value of x plus 2, and then we put a plus c. So now it seems that we have our solution with respect to finding the partial fraction decomposition of our original rational expression. So here we can actually differentiate this so that we can go back to the original answer, and that's not too bad, because we know that the derivative of natural log would just be 1 over x plus 1, and so on, right? And then of course you can add by using common denominators and things like that. Now, one thing that I will point out is that notice that when we solve for the b, right, we plugged in -1 because that canceled this factor, that factor. We plugged in -2, and that canceled out this factor, right? And it gave us c. But notice that in any case, what were we left finding? We were actually left with finding what a was equal to. But how about this? What if you had multiplied the a and the x all together? Well, you would get ax squared, right? But over here, what about over here? Wouldn't you get also cx squared? But see, like how there is no x squared over here. So that would mean that these two added must equal to 0x squared, which of course gives you that a plus c equals to 0. Now in any case, we already knew what c was. It was -3. By that form, we have that a minus 3 equals to 0, so a equals to 3. So we get a by completing something called fishing, where we just kind of go ahead and distribute, and we try to look at the left-hand side. Similarly, you could probably do the same thing where we find all the x terms and just say that it's equal to 2. If we look for the constant, well, the constant is this equation, isn't it? Where we just plug in 0 and we get that this has to equal to the constant. So in either case, like the only one that you would need to look for would be the 2x technically, right? But that defeats the whole purpose of skipping the part where we said that we don't like to FOIL it out, group the x squares, group the x's, and group the constants together to create a system of equations, of which, in that case, how do you solve a system of equations? Substitution, elimination, Gauss-Jordan method, Kramer's rule, inverse method, and I guess you could put the calculator on one of those methods, but in any case, that leads you down a type of rabbit hole that, you know, goes beyond the scope of this course, which in this case would be linear algebra, which, you know, is not too bad, but, you know, if it's going to be less computationally expensive, then this method is probably preferred that we continue to plug in strategic values. Note that you needed 3 values, hence 3 x values that you plug in. Because this equal sign is actually pretty powerful in the sense that as long as this equality does hold, we can plug in anything. We can plug in anything, actually. Because if we plug in really any value, then in this case, we'll still get what the unknowns technically are in any case. But another method that you could probably explore, perhaps, is maybe like what happens if we differentiate this, for example. Is the process going to change, you know, like, is it going to change the solutions? And the answer would be no. But be careful that, you know, maybe differentiation might be what one might call overkill. But you'll notice that it does technically work in some cases, of which I'll leave that to you to work on, you know, like, you know, whether you want to keep plugging in values, or do you want to FOIL, group the x's, group the constants, and any other higher order x's, and then you get a system of equations. Or maybe you want to fish around and see what you can extrapolate from the right-hand side, and then solve it from there. Either way, you know, okay, yeah, we just need to get the right answer, right?